Hello, and welcome to the Sleepy Astronomer. Tonight, we're meeting 3i Atlas through 100 carefully chosen facts, a cosmic visitor that represents only the third confirmed interstellar object ever detected in our solar system. This wanderer has travelled for millions of years through the darkness between stars, and now, for a brief cosmic moment, it graces our solar system with its presence. If you're settling in for the first time, welcome aboard our journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Wherever you are tonight, settling in for rest or simply curious about our cosmic visitor, I'm so glad you're here. Where in the world are you listening from tonight? If this journey through the facts of interstellar space helps you unwind or fills you with quiet wonder, feel free to like the video and subscribe for more gentle explorations of cosmic visitors, deep space, and sleep. Tonight's journey unfolds as 100 discoveries about this remarkable visitor, facts that become windows into larger truths about the cosmos. We'll begin with 3i Atlas's detection, follow its recognition as an interstellar traveller, and explore what its presence teaches us about comets, other star systems, and our place within the galaxy. Each fact we'll explore represents years of careful observation by astronomers around the world. From initial detection by robotic telescopes to detailed follow-up observations with space-based instruments, every piece of information about 3i Atlas has been hard-won through humanity's patient study of the cosmos. Interstellar objects like 3i Atlas are natural time capsules, preserving materials and conditions from the early days of other star systems. In studying this visitor, we're conducting archaeology on a cosmic scale, examining artifacts that may be older than our entire solar system. So, find your most comfortable position and let's begin our gentle journey through 100 facts that paint the portrait of a visitor from the stars. Facts that become stories, numbers that reveal wonder, and discoveries that connect us to the vast community of worlds that populate our galaxy. Out there, moving at tens of kilometers per second through our solar system, 3i Atlas continues its ancient journey, patient, mysterious, and beautiful, ready to share the secrets it has carried across the light years from its distant birthplace among alien suns. Our story begins on a summer evening in 2025, when robotic telescopes scanning the southern sky captured light from an object that would soon rewrite our understanding of interstellar visitors. The discovery moment itself was unremarkable, just another faint smudge among millions of observations recorded that night, but within hours, this unassuming detection would reveal itself as something extraordinary, our third confirmed messenger from the space between stars. The Asteroid Terrestrial Impact Last Alert System, known to astronomers simply as ATLAS, made the discovery on July 1, 2025, from its mountaintop observatory in Chile. Picture these robotic sentinels scattered across our planet like cosmic lighthouses, their cameras sweeping methodically across the heavens night after night. ATLAS was designed as Earth's early warning system, a guardian scanning for potentially dangerous asteroids that might threaten our world. These telescopes operate with a kind of mechanical devotion, never sleeping, never tiring, their electronic eyes constantly recording the positions of countless objects as they move through space. Each night, ATLAS captures thousands of images, each containing hundreds of thousands of stars and moving objects. Computer algorithms sift through this vast stream of data, looking for anything that appears in one image but not in the previous night's observations, or objects that have moved against the background of distant stars. It's a cosmic game of spot the difference played on an astronomical scale, where the prize might be early warning of an Earth-threatening asteroid, or, as in this case, the discovery of a visitor from another star system. But sometimes, in their patient vigil over our cosmic neighbourhood, these mechanical astronomers find something far more exotic than near-Earth asteroids. Sometimes they catch sight of wanderers from other star systems, objects that have travelled unimaginable distances through the darkness between stars before arriving in our solar system, like cosmic messages and bottles, carrying information about distant worlds we may never visit. The discovery came through what astronomers call a survey telescope, an instrument designed not to study individual objects in exquisite detail, but to watch vast swaths of sky and notice anything that moves or changes. It's rather like having a security camera that watches the entire night sky, recording everything and flagging anything unusual for further investigation. On that July evening, Atlas's wide-field camera captured 3I Atlas as little more than a moving point of light, barely distinguishable from the thousands of asteroids and comets that populate our solar system. The initial detection was so subtle that it required sophisticated computer algorithms to recognize it as something worth investigating. Among the millions of data points collected that night, 3I Atlas appeared as a faint smudge that moved slightly too fast and in slightly the wrong direction to be a typical solar system object. It would take days of careful follow-up observations and mathematical analysis before astronomers realized they were looking at something that had journeyed to us from the space between stars. The designation 3I carries profound significance in the story of cosmic exploration. That simple combination of number and letter announces to the astronomical community that here is only the third confirmed interstellar object ever observed, the third cosmic stranger to visit our solar system in all of recorded history. When astronomers assigned this designation to our visitor, they were acknowledging something remarkable, that in all our patient watching of the skies, from ancient civilizations tracking planets with the naked eye, to modern surveys monitoring millions of objects simultaneously, we have confirmed the arrival of only 3 visitors from beyond our solar system's borders. Think about that for a moment. Humanity has been watching the skies for thousands of years. We've catalogued hundreds of thousands of asteroids, discovered thousands of comets, tracked the movements of planets and moons, and mapped the positions of billions of stars. Yet, in all that time, all that careful observation, we've detected only 3 objects that originated beyond our solar system's gravitational embrace. 3 cosmic strangers in all of recorded history, each one a profound reminder of how vast and sparsely populated the galaxy truly is. The first interstellar visitor was ʻOumuamua, that mysterious elongated object discovered in 2017 that sparked intense debates about its nature and origin. This visitor was unlike anything astronomers had seen before, cigar-shaped, tumbling end over end, and showing a slight acceleration that couldn't be explained by gravitational forces alone. Some researchers wondered if its unusual properties might indicate artificial origins, though most scientists concluded it was likely a natural object with characteristics unlike anything in our solar system. ʻOumuamua's brief visit lasted only a few months before it disappeared back into interstellar space, leaving behind more questions than answers. The second was 2I Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, using a telescope he built himself in his backyard observatory in Crimea. Borisov appeared more comet-like and familiar than ʻOumuamua, developing a visible coma and tail as it approached the Sun, behaving much like the comets that originate in our own solar system's outer reaches. This visitor helped establish patterns for recognizing these cosmic wanderers and suggested that interstellar space might be filled with objects similar to those we find in our own cosmic neighborhood. 3i Atlas joins this exclusive club of interstellar visitors, each one representing a cosmic milestone in human discovery. Together, these three objects represent our only direct samples of matter from other star systems, cosmic ambassadors carrying chemical signatures from stellar nurseries we may never reach. They connect us to the broader galactic community in the most tangible way possible, through actual physical matter that has journeyed across the light years to reach our cosmic doorstep. The speed at which 3i Atlas was recognized as something special speaks to how dramatically astronomical discovery has evolved in recent decades. Where previous generations of astronomers might have taken weeks or months to confirm an unusual discovery, modern telescopes and computer systems can process enormous amounts of data almost instantly, calculating orbital parameters and sharing results across the global astronomical community in real time. Within days of the initial detection, astronomers around the world had confirmed 3i/Atlas's interstellar nature through careful measurements of its trajectory and velocity. This rapid confirmation was possible because of the international networks of telescopes and observers that now monitor the sky continuously. When Atlas detected something unusual, alert systems immediately notified observatories around the world, triggering a coordinated follow-up campaign that involved dozens of telescopes across multiple continents. This global response demonstrates how modern astronomy operates as a truly collaborative enterprise, where discoveries are shared instantly and resources are coordinated to maximize our understanding of rare cosmic events. Pre-discovery observations soon emerged, extending the observational record back to June 14, 2025. These earlier detections, initially overlooked in the vast stream of data collected by survey telescopes, became valuable once astronomers knew what to look for. It's rather like finding earlier photographs of a person in your family album once you know who you're looking for. The images were always there, but they only gained significance in hindsight. These pre-discovery observations allowed astronomers to extend 3i Atlas's observational arc, providing crucial additional data points for calculating its precise orbit and confirming its interstellar origin. The process of finding these earlier observations involved combing through terabytes of archival data, searching for any trace of 3i Atlas's passage through the inner solar system. The Zwicky Transit Facility in California found observations from late June 2025 within hours of the initial discovery announcement. Amateur astronomer Sam Dean identified additional Atlas pre-discovery observations stretching back to early June. These earlier sightings revealed that 3i/Atlas had been visible to Earth-based telescopes for weeks before anyone recognized its extraordinary nature, quietly moving through the constellation Sagittarius like any other faint asteroid. The reason 3i Atlas wasn't discovered earlier illustrates one of the ongoing challenges of modern astronomy. The comet was passing in front of the dense star fields of the galactic center, where the Milky Way's bright central bulge creates a crowded backdrop of stars that can mask the presence of faint moving objects. It's like trying to spot a specific person in a crowd during a busy festival. The object you're looking for might be clearly visible, but the sheer number of background sources makes it easy to overlook. This region of sky, rich with the light of billions of stars concentrated toward our galaxy's center, represents both a treasure trove for astronomers studying stellar populations and a challenging environment for detecting faint moving objects. The algorithms that search for new asteroids and comets must distinguish between genuine moving objects and the countless artifacts created by crowded star fields, cosmic ray hits on detectors, and other sources of false signals. Amateur astronomers played a crucial role in the follow-up observations that confirmed 3I Atlas's interstellar nature. Within days of the discovery announcement, backyard astronomers around the world were turning their telescopes toward this cosmic visitor, contributing valuable observations that helped refine its orbital parameters. This collaboration between professional observatories and amateur enthusiasts represents one of astronomy's great democratizing traditions, the recognition that important discoveries can come from anyone with the patience to watch the skies and the dedication to make careful observations. The amateur astronomy community's response to 3I Atlas demonstrates how citizen science continues to play a vital role in modern astronomical research. While professional surveys like Atlas discover most new objects, amateur astronomers provide essential follow-up observations, often using equipment they've built themselves and observing from locations around the world that provide different viewing angles and timing. Their contributions help create the comprehensive observational database needed to precisely characterize objects like 3I Atlas. The international nature of the confirmation process demonstrates how modern astronomy operates as a truly global enterprise, transcending national boundaries and political divisions in the pursuit of cosmic understanding. Observations from Chile provided the initial detection, while follow-up measurements came from telescopes in Hawaii, Arizona, Spain, and observatories around the world. Within 24 hours, this cosmic visitor had been observed from multiple continents, its interstellar nature confirmed by an international community of astronomers working together across time zones and national boundaries. This global collaboration reflects the universal human fascination with cosmic discovery. When something truly rare appears in our skies, the astronomical community responds with remarkable unity and efficiency, pooling resources and expertise to maximize our understanding of these precious opportunities. The discovery of 3I Atlas triggered this same international response, with observatories from the Americas to Europe to Asia, all contributing observations to the growing database of information about our latest interstellar visitor. As calculations progressed and more observations accumulated, the remarkable nature of 3I Atlas became increasingly clear. This wasn't simply another asteroid or comet from the outer reaches of our solar system. The mathematics of its trajectory told an unmistakable story of interstellar origin. There's something beautifully decisive about mathematics when it comes to cosmic visitors. As astronomers calculated 3I Atlas's path through space, the numbers told a story that was both precise and profound. The orbit wasn't elliptical, like the comfortable, repeating paths that planets and asteroids follow around our Sun. Instead, it traced a hyperbola, a mathematical curve that opens outward like cosmic parentheses, never closing, never returning. This single geometric fact revealed something extraordinary. Here was an object that had journeyed to us from the space between stars, following a trajectory that would carry it past our Sun and onward into the galaxy beyond, never to return to our cosmic neighborhood again. The object was moving too fast and following too steep a path to be bound by our Sun's gravity. Here was definitive proof of a visitor from the space between stars, confirmed not by speculation or wishful thinking, but by the unambiguous language of celestial mechanics. The initial uncertainty about whether 3I Atlas was an asteroid or a comet reflects how difficult it can be to characterize objects at great distances. Early observations showed no obvious signs of cometary activity, no visible coma or tail to indicate sublimating ice. Various astronomers, including the experienced comet hunter Alan Hale, reported seeing only a star-like point of light, indistinguishable from the rocky asteroids that populate the inner solar system. But this apparent simplicity was misleading, a reminder that the cosmos often reveals its secrets gradually, requiring patience and persistent observation. On July 2nd, just one day after the discovery, multiple observatories began detecting the telltale signs of cometary activity that would transform our understanding of this visitor. The Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope on Mauna Kea all reported seeing a marginal coma, a faint, fuzzy envelope of gas and dust surrounding the nucleus. This was the signature of sublimating ice, the calling card of a true comet beginning to respond to the sun's warming influence as it journeyed deeper into our solar system. The development of this coma represents one of the most beautiful processes in the solar system, the gradual awakening of a comet as it approaches the sun. For millions of years, 3I Atlas had been a frozen, inactive chunk of ice and rock drifting through the near absolute zero temperatures of interstellar space. But as it entered our solar system and began to feel the sun's warmth, even from billions of kilometers away, the most volatile ices on its surface began to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation process creates not just the visible coma, but also the subtle rocket-like forces that can slightly alter a comet's trajectory. As gas escapes from the nucleus, it carries away dust particles and creates a gentle thrust that can nudge the comet slightly off its predicted path. For 3I Atlas, these non-gravitational forces would prove to be remarkably subtle, suggesting a composition dominated by less volatile materials than many solar system comets. The Minor Planet Center, the international organization responsible for tracking small bodies in the solar system, officially announced the discovery on July 2, 2025. This announcement marked a pivotal moment in the story of 3I Atlas, the formal recognition by the global astronomical community that humanity had detected its third confirmed interstellar visitor. By that time, the MPC had collected 122 separate observations of the comet from 31 different observatories around the world, a remarkable testament to the speed and efficiency of modern astronomical follow-up. The rapid accumulation of observations reflects the extraordinary international cooperation that characterizes modern astronomy. Within hours of the initial discovery announcement, telescopes across multiple continents were turning toward this cosmic visitor. Observatories in Hawaii captured it as it set in their western sky, while European telescopes picked up the observation as 3I/Atlas rose in their eastern sky. This seamless handoff between observatories allowed for nearly continuous monitoring during the crucial early days when astronomers were working to confirm the object's interstellar nature. The MPC gave 3I Atlas both an interstellar object designation and a more traditional comet designation, C/2025 N1, Atlas. This dual nomenclature reflects the unique nature of interstellar comets. They are simultaneously members of the exclusive club of confirmed interstellar objects and participants in the more familiar family of comets that astronomers have been studying for centuries. The C designation indicates a non-periodic comet, while 2025 N1 shows it was the first comet discovered in the second half of July 2025, and Atlas honors the survey that made the discovery. Observations by David Jewett and Jane Liu using the Nordic Optical Telescope confirmed that 3I Atlas was clearly active, with a diffuse appearance characteristic of an outgassing comet. These astronomers brought particular expertise to the observation, having previously studied two Borisov and other unusual solar system objects. Their confirmation helped establish that 3I Atlas was indeed behaving like a comet, not just an asteroid that happened to have an interstellar trajectory. Miguel Alarcón and his team at the Instituto de Astrofísica de Canarias, using the 2-meter twin telescope at Teide Observatory, independently confirmed cometary activity on the same date. The fact that multiple research groups using different telescopes and observing techniques all reached the same conclusion about 3I Atlas's cometary nature provided strong evidence that this was a genuine detection rather than an instrumental artifact or observational error. Multiple telescopes showed that the comet's developing coma had a reddish color indicative of dust particles, similar to what had been observed in the previous interstellar comet 2, Borisov. This reddish coloration comes from organic compounds called tholins, complex molecules that form when simpler organic materials are exposed to radiation over long periods. The presence of these compounds suggests that 3I Atlas, like 2I Borisov, contains organic materials that may provide clues about the chemical processes occurring in other stellar systems. The speed of these confirmations reflects not just technological advancement, but the excitement that grips the astronomical community when something truly rare appears in our skies. Interstellar objects are so uncommon that their discovery triggers an immediate, coordinated response from observatories worldwide. Everyone wants to contribute to understanding these cosmic messengers while they remain visible and accessible to Earth-based telescopes. The window of opportunity for studying interstellar objects is relatively brief. They appear, grace us with their presence for a few months or years, and then continue their journeys into the depth of space, never to return. As 3I Atlas revealed its cometary nature through the development of a coma and the subtle signs of outgassing activity, it joined 2I Borisov in confirming that interstellar space contains populations of comet-like objects similar to those in our own solar system. This was reassuring in its own way, evidence that the processes of planetary system formation might follow similar patterns around different stars, creating similar types of small bodies that can be ejected into interstellar space through gravitational interactions with planets or stellar companions. The discovery also demonstrated the maturation of our ability to detect and characterize interstellar objects. When ʻOumuamua was discovered in 2017, it caught astronomers somewhat unprepared. By the time its interstellar nature was confirmed, it was already heading back toward interstellar space, limiting the time available for detailed study. The discovery of 2I Borisov came earlier in its passage through the solar system, allowing for more comprehensive observations. With 3I Atlas, the detection and confirmation process has become even more efficient, providing astronomers with maximum opportunity to study this rare visitor. The community effort to characterize this visitor demonstrates how 21st century astronomy operates as a collaborative international enterprise where discoveries are shared instantly and follow-up observations are coordinated across the globe. Social media and instant messaging systems allow astronomers to share preliminary results and coordinate observations in real time, creating a global network of observers that can respond to rare events like interstellar object discoveries with unprecedented speed and efficiency. Within 48 hours of the initial detection, 3I Atlas had transformed from an unknown point of light into a well-characterized interstellar comet with a growing database of observations from dozens of telescopes. This rapid progression from discovery to confirmation to detailed characterization represents the culmination of decades of technological advancement and international cooperation in astronomy. The robotic surveys that detected 3I Atlas, the rapid response networks that confirmed its nature, and the global community of observers that continue to track its progress, all represent humanity's collective effort to understand our place in the cosmic community and to welcome the rare visitors that journey to us from the space between stars. In the story of 3I Atlas's discovery, we see reflected our species' insatiable curiosity about the universe and our remarkable ability to work together across national and cultural boundaries in pursuit of cosmic understanding. Now that we've followed the remarkable story of 3I Atlas's discovery and recognition as our third interstellar visitor, let's turn our attention to the object itself, this cosmic wanderer that has journeyed across the light years to grace our solar system with its presence. What emerges from careful observation is a portrait of a comet unlike any other we've encountered, carrying within its frozen nucleus the chemical signatures of another star system and revealing secrets about the diversity of worlds that exist beyond our cosmic neighborhood. The nucleus of 3I Atlas, the solid icy heart around which everything else revolves, presents astronomers with a fascinating puzzle. Early estimates suggested this cosmic visitor might be quite large, perhaps 20 kilometers across, roughly the size of a small city or a substantial mountain. But as observations accumulated and analysis techniques improved, these estimates began to shrink. By late July 2025, using data from the Vera Rubin Observatory in Chile, astronomers had revised the size estimate downward to about 10 kilometers in diameter. The Hubble Space Telescope, humanity's most famous orbital observatory, provided even more precise measurements that further refined our understanding of this visitor's dimensions. Using Hubble's exquisite resolution and sensitivity, astronomers determined that 3I Atlas's nucleus measures no more than 5.6 kilometers across at its widest point, roughly the distance you might walk in an hour on a leisurely stroll. But the measurements also revealed something intriguing. The nucleus could be even smaller, perhaps as little as 440 meters in diameter, no larger than a modest hill or a few city blocks. This uncertainty in size estimates reflects one of the fundamental challenges of studying distant objects in space. When you're trying to measure something millions of kilometers away that produces no light of its own, you're essentially trying to determine the size of a charcoal briquette by the amount of sunlight it reflects while suspended in a vast, dark room. The brightness we observe depends not just on the object's size, but also on how reflective its surface is, what angle we're viewing it from, and how much dust and gas might be obscuring our view. What we can say with confidence is that 3I Atlas represents a relatively substantial object by the standards of interstellar visitors. When ʻOumuamua passed through our solar system in 2017, it measured perhaps 400 meters in length, large enough to be impressive, but small enough that it might have been just a fragment broken off from a larger body. 3I Atlas, even at the smaller end of current size estimates, represents a more substantial chunk of matter, a genuine piece of another planetary system rather than merely a cosmic pebble. The shape of 3I Atlas remains largely mysterious, hidden beneath the growing envelope of gas and dust that surrounds active comets. Unlike ʻOumuamua, which revealed its elongated, cigar-like profile through careful analysis of its brightness variations, 3I Atlas's developing coma makes it difficult to discern the precise contours of the underlying nucleus. What we see when we point telescopes toward this visitor is not the sharp, well-defined outline of a rocky asteroid, but the fuzzy, diffuse glow of a comet coming to life. As 3I Atlas tumbles through space in its long, solitary journey, it performs a gentle cosmic dance, rotating slowly against the star-filled darkness. This rotation creates a subtle lighthouse effect that astronomers can detect from across the solar system. As different parts of the comet's irregular surface catch and reflect sunlight, 3I Atlas grows slightly brighter, then dimmer, then brighter again, in a rhythm that speaks to its spinning motion. It's rather like watching a distant campfire flicker as someone slowly turns a log, except this particular ember has been turning for millions of years as it drifted between the stars and will continue its patient rotation long after it leaves our solar system behind. The rotation period of 3I Atlas, how long it takes to complete one full spin, remains under careful study. Determining this seemingly simple property requires weeks or months of patient observation, carefully measuring tiny changes in brightness and looking for repeating patterns that might reveal the comet's rotation rate. Some comets spin rapidly, completing a rotation in just a few hours, while others tumble more slowly, taking days to turn once around their axis. The colour of 3I Atlas tells its own story about the materials from which this visitor is composed. Multiple telescopes have confirmed that the comet displays a distinctly reddish hue, particularly in its growing coma of gas and dust. This coloration isn't the vibrant red of a rose or a sunset, but a subtle, earthy reddish-brown that speaks to the presence of complex organic molecules that have been slowly cooking in the radiation environment of interstellar space for millions of years. This reddish coloration comes from organic compounds called tholins, complex hydrocarbon molecules that form when simpler organic materials like methane and nitrogen are exposed to ultraviolet radiation and cosmic rays over long periods. These compounds are found throughout the outer solar system, giving many moons and small bodies their characteristic rusty reddish appearance. The fact that 3I Atlas displays similar coloration suggests that the chemical processes occurring in interstellar space mirror those we observe in our own cosmic neighbourhood. The presence of these organic compounds raises tantalizing questions about the chemical complexity that might exist in comets from other star systems. On Earth, organic molecules form the foundation of all life as we know it. While the tholins found in 3I Atlas are far simpler than the complex biochemistry of living organisms, they represent important stepping stones on the path from simple chemicals to the molecular complexity that might eventually support life. The coma surrounding 3I Atlas, that fuzzy envelope of gas and dust that marks it as an active comet, has grown steadily as the visitor has approached the Sun. When first detected in early July 2025, any cometary activity was so subtle as to be nearly undetectable. But as 3I Atlas continued its inward journey, the warming effect of solar radiation began to sublimate increasing amounts of ice from its surface, creating an ever-expanding cloud of gas and dust that now spans tens of thousands of kilometers. To appreciate the scale of this coma, consider that it has grown to roughly twice the diameter of Earth, a cloud of gas and dust so large that our entire planet could fit comfortably inside it with room to spare. Yet this impressive envelope is also incredibly tenuous, containing less material than the best vacuum ever created in a terrestrial laboratory. It's a cloud so thin that if you could somehow fly through it, you might not even notice its presence except for the occasional dust particles striking your spacecraft's hull. High-resolution images from the Gran Telescopio Canarias, one of the world's largest optical telescopes, have revealed that this coma appears slightly elliptical rather than perfectly circular, measuring approximately 26,400 by 24,700 kilometers in diameter. This elongated shape might result from the comet's rotation, which could cause material to be preferentially ejected from certain regions of the nucleus, or from the direction and strength of the solar wind that helps shape the coma's outer boundaries. The angular size of this coma as seen from Earth provides another perspective on the vast distances involved in our solar system. Despite spanning tens of thousands of kilometers, 3I Atlas's coma appears as a tiny, fuzzy patch only about 2 arc-seconds across to the most sensitive telescopes, roughly the apparent size of a quarter viewed from 2.5 miles away. This reminds us that even objects spanning the diameter of Earth appear minuscule when viewed across the hundreds of millions of kilometers that separate us from this interstellar visitor. As 3I Atlas approaches the Sun and its surface temperature gradually increases, this coma continues to grow and evolve. Pre-discovery observations by the Vera Rubin Observatory showed that the coma had expanded from about 13,040 kilometers across on June 21st to 18,760 kilometers by July 2nd, a growth rate of several hundred kilometers per day as the comet responded to increasing solar heating. The material comprising this coma consists primarily of relatively large dust grains, several micrometers in radius, tiny by human standards, but substantial compared to the submicron particles that dominate the comas of many solar system comets. These dust grains scatter sunlight efficiently, creating the visible glow that allows us to observe the coma from Earth. Mixed with these dust particles are various gases sublimated from the comet's icy nucleus: water vapor, carbon dioxide, carbon monoxide, and perhaps more exotic compounds that will reveal themselves to spectroscopic analysis as 3I Atlas continues its approach to the Sun. The composition of these gases holds particular scientific interest because they provide direct samples of materials from another star system. Every molecule sublimating from 3I Atlas's nucleus carries chemical signatures that reflect the conditions present in its birthplace billions of years ago. By analyzing the ratios of different isotopes, versions of elements with different numbers of neutrons, astronomers can potentially determine whether this visitor formed in an environment similar to our own solar system or under different conditions that might reveal alternative pathways for planetary system formation. Spectroscopic observations have begun to reveal the chemical fingerprints of 3I Atlas's outgassing. The reddish color of its coma indicates the presence of carbon-bearing compounds, while future observations with more sensitive instruments may detect water vapor, carbon dioxide, and other molecules that sublimate as the comet continues to warm. These observations will be compared with similar measurements of comets from our own solar system to determine whether interstellar comets share the same basic composition as their solar system cousins. The velocity at which 3I Atlas travels through space represents one of its most remarkable characteristics. When discovered, this interstellar visitor was moving at approximately 60 kilometers per second relative to the Sun, fast enough to travel from New York to Los Angeles in less than 2 minutes. This extraordinary speed immediately marked 3I Atlas as something special, as it far exceeds the velocities typical of solar system objects in the inner solar system. This speed has been steadily increasing as 3I Atlas falls deeper into the Sun's gravitational well, accelerating under the influence of our star's immense mass. As it reaches its closest approach to the Sun in late October 2025, 3I/Atlas will be travelling at nearly 25,000 kilometers per hour, fast enough to circumnavigate Earth's equator in less than 2 hours. This acceleration follows the same gravitational principles that govern all objects in the solar system, but the extreme initial velocity ensures that 3I Atlas will easily escape the Sun's gravitational influence and continue its journey into interstellar space. The trajectory that 3I Atlas follows through our solar system tells the story of its interstellar origins with mathematical precision. Astronomers can trace this path backward in time, calculating where the comet has been and attempting to determine its approximate direction of origin in the galaxy. These calculations suggest that 3I Atlas approached our solar system from the general direction of the constellation Sagittarius, which happens to be the direction toward the center of our galaxy. This doesn't necessarily mean that 3I Atlas originated near the galactic center. The comet has been traveling for so long that its motion has been influenced by the gravitational effects of many stars and the overall galactic rotation. Over millions of years, the original trajectory has been bent and twisted by countless gravitational encounters, making it nearly impossible to determine the specific star system where this visitor began its journey. What astronomers can determine is that 3I Atlas belongs to what they call the thick disk population of our galaxy, objects with orbital motions that are tilted relative to the main galactic plane, and that tend to be older than the typical stars and gas clouds in our cosmic neighborhood. This suggests that 3I Atlas may be quite ancient, possibly forming when our galaxy was younger and had a different structure than it displays today. Recent studies have attempted to estimate the age of 3I Atlas based on its orbital characteristics and the typical ages of thick disk objects. These calculations suggest that this cosmic wanderer may be between 7.6 and 14 billion years old, making it potentially older than our entire solar system, which formed 4.6 billion years ago. If these age estimates are correct, 3I Atlas represents a fossil from an earlier epoch of galactic history, a time capsule carrying materials and memories from when the universe was young. The surface properties of 3I Atlas remain largely hidden beneath its growing coma, but astronomers can infer some characteristics from the way it reflects sunlight and responds to solar heating. The comet appears to have a relatively low albedo, meaning it reflects only a small percentage of the sunlight that strikes it. This dark surface is typical of comets throughout the solar system, which tend to be among the darkest objects we know, reflecting less light than charcoal or soot. This low reflectivity results from the presence of complex organic compounds and rocky materials that have been altered by eons of exposure to cosmic radiation. As comets age and their surface ices sublimate away, they develop a dark, carbon-rich crust that protects the interior ice from further sublimation while absorbing most of the sunlight that strikes them. This process creates what astronomers call a dirt layer that can significantly slow the rate of outgassing as a comet approaches the Sun. The fact that 3I Atlas shows clear signs of cometary activity despite its dark surface suggests that its journey through interstellar space has not completely desiccated its nucleus. Somewhere beneath that dark crust lies a reservoir of frozen volatiles, water ice, carbon dioxide ice, and perhaps more exotic compounds that continue to sublimate as the comet warms. This preservation of volatile materials over millions of years of interstellar travel speaks to the effectiveness of cometary nuclei as cosmic refrigerators, maintaining samples of ancient ice in the deep freeze of space. As 3I Atlas continues its passage through our solar system, it will reach its closest approach to the Sun, called perihelion, in late October 2025. At that point, it will be about 1.4 astronomical units from the Sun, roughly 130 million miles, placing it just inside the orbit of Mars. This represents a comfortable distance that will allow the comet to warm and outgas without risking the complete destruction that might result from a closer solar encounter. Even at this closest approach, 3I Atlas will never pose any threat to Earth. The comet's trajectory will keep it at least 1.8 astronomical units away from our planet, about 170 million miles, or roughly twice the distance between Earth and the Sun. This safe distance ensures that we can observe this interstellar visitor without any concern for its gravitational influence on our world, while still being close enough for detailed telescopic study. The predictable nature of 3I Atlas's trajectory also means that astronomers worldwide can plan coordinated observation campaigns to maximize our scientific return from this rare visitor. Ground-based telescopes will track the comet's approach and monitor changes in its activity level, while space-based observatories like the Hubble Space Telescope and the James Webb Space Telescope will provide high-resolution images and detailed spectroscopic analysis of its composition. The opportunity to study an interstellar comet in detail is so rare that virtually every major astronomical facility on Earth and in space has contributed observations to the growing database of information about 3I Atlas. This coordinated effort represents one of the largest international collaborations in astronomical history, bringing together researchers from dozens of countries and institutions in a common effort to understand this messenger from another star system. The process by which astronomers determine these physical properties represents a remarkable feat of detective work, extracting precise information about an object millions of kilometers away using nothing but the faint light it reflects and emits. When 3I Atlas was first detected, it appeared as little more than a faint smudge, barely distinguishable from background noise in the telescope's detector. Transforming this weak signal into detailed knowledge about the comet's size, composition, and behavior requires sophisticated techniques developed over decades of astronomical research. Photometry, the precise measurement of an object's brightness, forms the foundation of most physical characterization. By observing 3I Atlas through different colored filters, astronomers can determine not just how bright it appears, but how that brightness varies with wavelength. This color information reveals the composition of both the nucleus and the surrounding coma, as different materials reflect and absorb light in characteristic ways. The challenge of measuring 3I Atlas's true size illustrates the complexities involved in studying distant objects. When astronomers observe the comet, they're not seeing the nucleus directly, but rather the combined light from both the solid nucleus and the surrounding coma of gas and dust. Separating these two components requires careful modeling of how cometary comas scatter sunlight, taking into account the size distribution of dust particles, their composition, and the geometry of the observation. Different wavelengths of light penetrate the coma to different depths, allowing astronomers to probe various layers of the cometary atmosphere. Blue light tends to be scattered more strongly by small dust particles, while infrared light can penetrate deeper into the coma and potentially reveal thermal emission from the nucleus itself. By combining observations across multiple wavelengths, researchers can build up a three-dimensional picture of the comet's structure and activity. The development of adaptive optic systems has revolutionized ground-based observations of objects like 3I Atlas. These sophisticated systems use deformable mirrors to compensate for the blurring effects of Earth's atmosphere, allowing ground-based telescopes to achieve image quality that rivals space-based observatories. When applied to cometary observations, adaptive optics can resolve fine structure within the coma and potentially detect jets of material emanating from specific regions of the nucleus. Spectroscopy, The analysis of light spread out into its component wavelengths provides the most detailed information about 3I Atlas's composition. When molecules in the comet's coma absorb or emit light at specific wavelengths, they create spectral lines that serve as fingerprints for different chemical compounds. Water vapor produces characteristic absorption lines in the infrared, while carbon-bearing molecules create features in both the visible and infrared parts of the spectrum. The Transiting Exoplanet Survey Satellite, TESS, originally designed to search for planets around other stars, has provided valuable observations of 3I Atlas that extend back to May 2025, 2 months before the comet's official discovery. TESS's wide-field cameras and precise photometry revealed that the comet may have been showing signs of activity much earlier than initially thought, when it was still roughly 6.4 astronomical units from the Sun, farther than Jupiter's distance from our star. This early activity suggests that 3I Atlas contains particularly volatile materials that begin sublimating at very low temperatures, or that the comet's structure allows subsurface ice to reach the surface more easily than in typical solar system comets. The fact that cometary activity was detectable at such a large distance from the Sun speaks to either the comet's size, its composition, or both. Larger comets have more surface area for sublimation, while comets rich in volatile materials like carbon monoxide can remain active at greater distances than those dominated by water ice. Radio observations provide another window into 3I Atlas's composition and behavior. As the comet approaches the Sun and its outgassing rate increases, radio telescopes may be able to detect emission lines from various molecules in the coma. These observations are particularly valuable because radio waves can penetrate dust that might obscure optical observations, providing information about the gas composition even if the visual appearance becomes dominated by dust scattering. The Atacama, large millimeter/submillimeter array, or ALMA in Chile, represents one of the most powerful tools for studying the molecular composition of comets. ALMA's high sensitivity and resolution could potentially detect dozens of different molecular species in 3I Atlas's coma, from simple molecules like water and carbon monoxide to complex organic compounds that might provide clues about prebiotic chemistry in other star systems. Future observations as 3I Atlas approaches perihelion will test whether its activity follows the same patterns seen in solar system comets. Most comets show a predictable increase in brightness and outgassing rate as they approach the Sun, following what astronomers call a power law relationship between solar distance and activity level. Any deviations from this expected behavior could reveal differences in composition or internal structure that reflect the comet's interstellar origins. The possibility of outbursts or fragmentation events adds another layer of complexity to 3I Atlas's future evolution. Some comets experience sudden increases in brightness when subsurface pockets of volatile material are exposed to solar heating, creating dramatic jets of gas and dust that can temporarily increase the comet's apparent brightness by factors of 10 or more. While no such outbursts have been observed in 3I Atlas as of August 2025, the possibility remains as the comet continues to warm. Fragmentation represents a more dramatic possibility, where tidal forces or internal pressure from sublimating ice could break the nucleus into multiple pieces. The breakup of comet Shoemaker-Levy 9 into multiple fragments before its collision with Jupiter demonstrated how even relatively small gravitational forces can overcome the weak internal cohesion of cometary nuclei. If 3I Atlas were to fragment, it would provide an unprecedented opportunity to study the internal structure of an interstellar comet. The James Webb Space Telescope, with its unprecedented infrared sensitivity, will provide detailed spectroscopic observations of 3I Atlas that could revolutionize our understanding of interstellar comet composition. Webb's instruments can detect water vapor, carbon dioxide, carbon monoxide, methane, and numerous other molecules with exquisite precision, potentially revealing exotic compounds that have never been detected in solar system comets. Infrared observations are particularly valuable for cometary studies because many important molecules have their strongest spectral features in the infrared part of the spectrum. Water vapor, the most abundant volatile in most comets, produces prominent absorption bands in the near-infrared that can be used to measure the comet's water production rate. Carbon dioxide, often the second most abundant volatile, creates distinctive features in the mid-infrared that are easily detected by sensitive instruments. The European Space Agency's Comet Interceptor mission, currently under development, represents an ambitious attempt to study an interstellar comet up close. While this mission won't reach 3I Atlas, it's designed to intercept future long-period comets or interstellar objects. The scientific techniques being developed for Comet Interceptor will inform how we might study similar objects in the future. The magnetic environment around 3I Atlas provides another avenue for study as the comet interacts with the solar wind, the stream of charged particles flowing outward from the Sun. As the solar wind encounters the comet's growing coma, it creates a complex interaction region where magnetic fields become tangled and particles are accelerated to high energies. Spacecraft missions to other comets have revealed that these interaction regions can extend for hundreds of thousands of kilometers around active comets. Ground-based radio telescopes can sometimes detect the radio emission produced when energetic electrons spiral through these magnetic fields, providing information about the comet's interaction with its space environment. These observations complement the optical and infrared studies by revealing how the comet's presence affects the local space environment and how that environment, in turn, shapes the comet's coma and tail development. Polarimetry, the measurement of polarized light reflected by the comet, offers insights into the size and composition of dust particles in the coma. When sunlight scatters off dust grains, it becomes partially polarized in a way that depends on the particle's size, shape, and composition. By measuring this polarization carefully, astronomers can determine whether the dust in 3I Atlas's coma consists of compact, rocky particles or fluffy, organic-rich aggregates. These polarimetric observations of 3I Atlas will be compared with similar measurements of solar system comets to determine whether interstellar comets produce dust with similar properties. Any differences could reveal variations in the dust formation processes or the conditions present during the comet's formation in another star system. The study of 3I Atlas also benefits from advances in machine learning and artificial intelligence that allow astronomers to extract maximum information from limited observations. Neural networks trained on observations of solar system comets can identify subtle patterns in 3I Atlas's behavior that might not be apparent to human observers, potentially revealing new insights about its composition or activity patterns. Citizen science projects have also contributed to our understanding of 3I Atlas, with amateur astronomers around the world contributing observations that help fill gaps in the professional observational record. These contributions are particularly valuable for monitoring changes in the comet's brightness and appearance over timescales of days to weeks, providing continuous coverage that would be difficult to achieve with professional observatories alone. The thermal properties of 3I Atlas's nucleus remain largely mysterious, but they will become increasingly important as the comet approaches perihelion. Different materials conduct heat at different rates, affecting how quickly the comet responds to changes in solar heating. A nucleus composed primarily of ice might warm and begin outgassing quickly, while one dominated by rocky material might respond more slowly to increasing solar radiation. Thermal infrared observations, particularly those planned with the James Webb Space Telescope, may be able to detect heat emission from 3I Atlas's nucleus directly. These observations could reveal the comet's thermal inertia, a measure of how quickly it responds to changes in solar heating, which in turn provides clues about the thermal properties of the surface materials and the nucleus's internal structure. The rotation state of 3I Atlas influences virtually every aspect of its physical behavior, from the pattern of outgassing to the shape of the developing coma. If the comet rotates rapidly, centrifugal forces might preferentially eject material from equatorial regions, creating an asymmetric coma. If it tumbles chaotically, the outgassing pattern might vary unpredictably, creating complex structures in the surrounding gas and dust. Long-term photometric monitoring will eventually reveal 3I Atlas's rotation period, but this requires weeks or months of observations to detect the subtle brightness variations caused by the comet's changing orientation. The fact that these variations are often quite small, perhaps just a few % change in brightness, makes them challenging to detect against the background of other changes in the comet's appearance as its activity level evolves. As 3I Atlas continues its journey through our solar system, each new observation adds another piece to the puzzle of its nature and origins. The comet serves as a natural laboratory for studying materials and processes that occurred in another star system billions of years ago, preserved in the deep freeze of interstellar space and now revealed under the gentle warming of our Sun. The comprehensive study of this remarkable visitor represents one of the greatest opportunities in modern astronomy to understand the diversity of planetary systems and the common processes that shape matter throughout our galaxy. In the subtle dance of light and shadow, gas and dust that surrounds 3I Atlas, we find encoded the story of another world, another time, another chapter in the cosmic tale of how stars and planets and comets come to be. As we prepare to explore the deeper scientific significance of 3I Atlas in our next chapter, we carry with us this detailed portrait of a cosmic wanderer, an ancient visitor whose every photon of reflected light carries information about the diversity of worlds and the universal processes that shape matter across the galaxy. In studying the physical properties of this remarkable object, we're not just learning about a single comet, but glimpsing the fundamental unity underlying the apparent diversity of our cosmic environment. As we've traced the discovery and characterized the physical properties of 3I Atlas, we've been building towards something far more profound than the study of a single cosmic object. This interstellar wanderer represents a scientific treasure of extraordinary significance, a messenger from deep space and deep time that carries within its ancient nucleus information about the formation of planetary systems, the chemical evolution of our galaxy, and the fundamental processes that shape matter across billions of years of cosmic history. The rarity of confirmed interstellar objects cannot be overstated. In all of human history, across thousands of years of sky-watching and decades of systematic astronomical surveys, 3I Atlas represents only the third such visitor we have definitively identified. This scarcity makes each interstellar object extraordinarily precious to science, offering insights that would be impossible to obtain through any other means. We cannot travel to other star systems to study their planetary formation processes directly, but occasionally, as with 3I Atlas, samples from those distant systems journey to us. Consider the implications of this rarity. Our solar system contains hundreds of thousands of known asteroids and comets, remnants from its formation 4.6 billion years ago, that provide a detailed record of the processes that built our planetary system. Yet from the vast galaxy beyond, containing hundreds of billions of stars and potentially trillions of comets and asteroids, we have confirmed the arrival of only 3 visitors in recorded history. This speaks to both the immense scales involved in interstellar space and the remarkable fortune that allows us to study objects like 3I Atlas. Each confirmed interstellar visitor has fundamentally expanded our understanding of planetary systems and galactic evolution. ʻOumuamua challenged our assumptions about what small bodies from other star systems might look like, displaying an elongated shape and unusual acceleration that sparked debates about its composition and even its origin. 2I Borisov provided reassuring evidence that interstellar comets could behave much like their solar system counterparts, while also revealing subtle differences in composition that hinted at variations in planetary formation processes. 3I Atlas continues this story of discovery while adding new chapters to our understanding of interstellar objects. Its larger size compared to ʻOumuamua suggests that substantial objects can survive ejection from their birth systems and subsequent travel through interstellar space. Its cometary nature confirms that water ice and other volatile materials can persist during million-year journeys through the galaxy, preserving samples of ancient chemistry for eventual study when these wanderers encounter other star systems. The age estimates for 3I Atlas place it among the oldest objects ever studied by human science. Calculations based on its orbital characteristics and galactic dynamics suggest this cosmic visitor may be between 7.6 and 14 billion years old, potentially older than our entire solar system. If these estimates prove correct, 3I Atlas represents a direct sample of materials from the early universe, formed when our galaxy was younger and had a different structure than we observe today. To appreciate the significance of this age, consider that 3I Atlas may have formed when the universe itself was only half its current age. At that time, the Milky Way contained fewer heavy elements than it does today, as generations of stars had not yet lived and died to enrich the galactic environment with the products of stellar nucleosynthesis. The chemical composition of 3I Atlas therefore provides a window into the conditions present during an earlier epoch of galactic evolution. The thick disk population to which 3I Atlas likely belongs represents an ancient component of our galaxy's structure. These objects follow orbits that are tilted relative to the main galactic plane and tend to be older than the stars and gas clouds in the galaxy's thin disk where our Sun resides. Thick disk objects, formed during a period when the galaxy was more turbulent and dynamically active, possibly during interactions with smaller satellite galaxies that were accreted during the Milky Way's early growth. This galactic context adds layers of meaning to every observation of 3I Atlas. When we analyze its composition, we're not just learning about a single comet, but sampling the chemical environment that existed in our galaxy billions of years ago. When we study its orbital motion, we're tracing pathways through space and time that connect us to the dynamical history of the Milky Way itself. The isotopic composition of materials in 3I Atlas's coma will provide crucial tests of models for stellar nucleosynthesis and galactic chemical evolution. Different types of stars produce different ratios of isotopes, variants of elements with different numbers of neutrons, and these signatures become mixed into the interstellar medium where new stars and planetary systems form. By measuring isotope ratios in 3I Atlas and comparing them with solar system values, astronomers can determine whether this visitor formed in a chemical environment similar to our own or under conditions that reflect an earlier epoch of galactic evolution. Water isotope ratios prove particularly valuable for these studies. The ratio of deuterium, heavy hydrogen, to normal hydrogen varies depending on the temperature and chemical conditions present during water formation. Comets from the outer regions of our solar system show different deuterium ratios than those from the inner regions, reflecting the temperature gradient present in our solar nebula 4.6 billion years ago. The deuterium ratio in 3 ʻAtlas's water vapor will reveal whether its birth environment resembled our solar system's outer regions or displayed characteristics unique to an earlier epoch of planetary formation. Carbon isotope ratios provide another diagnostic tool for understanding 3 ʻAtlas's origins. Carbon-12 and carbon-13 are produced in different stellar environments and incorporated into planetary systems in varying proportions depending on the local stellar population. Measurements of carbon isotopes in 3 ʻAtlas's organic compounds could reveal whether this visitor formed in a region of the galaxy with a different stellar composition than our local environment. The organic chemistry preserved in 3 ʻAtlas represents one of its most scientifically valuable aspects. Comets are thought to have delivered significant quantities of organic compounds to the early Earth, potentially providing some of the raw materials from which life eventually emerged. By studying the organic molecules in an interstellar comet, astronomers can investigate whether the chemical building blocks of life are common throughout the galaxy, or whether Earth's biological chemistry reflects the unique conditions present in our particular stellar neighborhood. The detection of complex organic molecules in 3 ʻAtlas would have profound implications for astrobiology, the study of life in the universe. If comets from other star systems carry similar organic inventories to those in our solar system, it would suggest that the chemical pathways leading to biological complexity may be universal features of planetary system formation. Conversely, significant differences in organic composition might reveal that life's chemistry is more contingent on local conditions than previously thought. Spectroscopic observations planned for 3 ʻAtlas's approach to perihelion will search for a wide variety of organic compounds, from simple molecules like methane and carbon monoxide to complex hydrocarbons and potentially even amino acid precursors. The James Webb Space Telescope's unprecedented infrared sensitivity makes it capable of detecting organic molecules at concentrations far below what was possible with previous instruments. The preservation of volatile materials in 3 ʻAtlas, despite its ancient age and long journey through interstellar space, provides important insights into the physics of small body evolution. The fact that this comet still contains enough ice to create a substantial coma demonstrates the effectiveness of cometary nuclei as cosmic deep freezers, maintaining samples of ancient materials across billion-year timescales. This preservation also places constraints on the physical conditions present in interstellar space. The survival of volatile compounds requires that 3 ʻAtlas never experience temperatures high enough to completely sublimate its ice inventory during its journey between star systems. This suggests that the comet's trajectory avoided close encounters with other stars and remained in the cold depths of interstellar space for most of its journey. The radiation environment of interstellar space has clearly affected 3 ʻAtlas, as evidenced by the reddish coloration that indicates the presence of radiation-processed organic compounds. Cosmic rays, high-energy particles that permeate the galaxy, gradually alter the chemical composition of exposed surfaces, creating complex organic molecules called tholins that give many outer solar system objects their characteristic colors. The degree of radiation processing observed in 3 ʻAtlas provides information about both the duration of its interstellar journey and the intensity of cosmic ray exposure it experienced. Objects that spend longer in interstellar space or traverse regions with higher cosmic ray fluxes show more extensive radiation damage and redder coloration. The specific colors and spectral features observed in 3I Atlas will help astronomers reconstruct its journey through the galaxy. The study of 3I Atlas also contributes to our understanding of planetary system formation and evolution by providing constraints on the efficiency of small body ejection mechanisms. For interstellar objects to exist, they must first be ejected from their birth systems through gravitational interactions with planets or stellar companions. The properties of objects like 3I Atlas help astronomers understand how common such ejection events are and what types of objects are most likely to be scattered into interstellar space. Current models suggest that most ejected objects should come from the outer regions of planetary systems, where gravitational interactions can more easily accelerate small bodies to escape velocity. The composition and characteristics of 3I Atlas provide tests of these models, potentially revealing whether interstellar comets originated in environments similar to our own Kuiper belt, or from different regions of their birth systems. The orbital dynamics of 3I Atlas also provide insights into the structure and evolution of our galaxy. As this cosmic wanderer traveled through interstellar space, its trajectory was influenced by gravitational interactions with the stars and gas clouds it encountered, as well as by the overall gravitational field of the galaxy itself. The current orbital motion of 3I Atlas therefore carries information about the galactic environments it has traversed during its long journey. Astronomers can work backward from 3I Atlas's current trajectory to estimate its probable path through the galaxy over the past few million years. These calculations reveal the general direction from which the comet approached our solar system and provide clues about the regions of the galaxy where it may have spent time during its journey. While the exact birth location of 3I Atlas will likely remain unknown, these orbital studies can identify the broad galactic regions where it might have originated. The gravitational effects that shaped 3I Atlas's journey also influence the orbits of countless other objects in interstellar space. Computer simulations suggest that the galaxy may contain trillions of orphaned comets and asteroids wandering between star systems, most of them too faint and distant to be detected by current surveys. 3I Atlas provides a rare glimpse into this invisible population of interstellar debris, offering insights into a component of galactic mass that remains largely hidden from direct observation. Future deep sky surveys, particularly the Vera Rubin Observatory's Legacy Survey of Space and Time, are expected to detect dozens of interstellar objects each year once they begin full operations. This will transform the study of interstellar visitors, from the analysis of individual rare events to the statistical investigation of entire populations. The detailed characterization of 3I Atlas provides crucial groundwork for interpreting these future discoveries. The comparative study of multiple interstellar objects will eventually reveal whether the 3 visitors detected so far represent typical examples or unusual exceptions. Are most interstellar comets similar in size and composition to 2I Borisov and 3I Atlas, or do these objects represent just one end of a broader distribution? Do interstellar asteroids like ʻOumuamua represent a common population, or are they rare exceptions with unusual properties? The techniques developed for studying 3I Atlas will prove invaluable for characterizing future interstellar visitors. The rapid response networks that coordinated follow-up observations, the spectroscopic methods used to analyze its composition, and the theoretical frameworks developed to interpret its properties will all be applied to subsequent discoveries. Each new interstellar object will add to our understanding while benefiting from the lessons learned from previous visitors. The scientific legacy of 3I Atlas extends beyond the immediate results of current observations to the methodological advances that enable future discoveries, the development of automated detection algorithms, the coordination of international observing campaigns, and the integration of multi-wavelength observations all represent advances in astronomical practice that will enhance our ability to study rare cosmic phenomena. Educational and outreach efforts surrounding 3I Atlas have also played important roles in communicating the excitement of astronomical discovery to public audiences. The rarity and exotic nature of interstellar visitors capture public imagination in ways that help build support for scientific research and inspire new generations of astronomers and planetary scientists. The cultural impact of discovering objects from other star systems resonates with fundamental human questions about our place in the universe and our relationship with the cosmos beyond our solar system. These visitors serve as tangible reminders that Earth exists within a vast galactic community, connected to distant regions of space through the constant exchange of matter and energy that characterizes our dynamic galaxy. The interdisciplinary nature of 3I Atlas research demonstrates the connections between different fields of astronomy and planetary science. Understanding this visitor requires expertise in cometary physics, stellar evolution, galactic dynamics, astrochemistry, and observational techniques spanning the electromagnetic spectrum. The collaborative effort to study 3I Atlas brings together specialists from many subdisciplines, creating opportunities for cross-fertilization of ideas and methods. The technological challenges involved in characterizing 3I Atlas have driven advances in instrumentation and data analysis techniques that benefit astronomy more broadly. The need to extract maximum scientific information from limited observing opportunities has led to innovations in telescope scheduling, data processing algorithms, and statistical analysis methods that find applications in many areas of astronomical research. As 3I Atlas continues its passage through our solar system, approaching perihelion in late October 2025, the scientific opportunities will intensify. The increasing solar heating will drive higher rates of outgassing, making the comet's composition more accessible to spectroscopic analysis. The changing solar distance will also test theoretical models of cometary behavior and reveal whether interstellar comets respond to solar heating in the same ways as their solar system counterparts. The peak activity period around perihelion represents the optimal time for detecting trace constituents in 3I Atlas's coma that might be too faint to observe during its more distant approach. Molecules like hydrogen cyanide, formaldehyde, and methanol often become detectable only when comets are closest to the Sun and their outgassing rates reach maximum levels. The detection of these species in 3I Atlas would provide important constraints on the chemical conditions present in its birth environment. Long-term monitoring of 3I Atlas as it departs the solar system will provide insights into how cometary activity evolves during the transition from solar heating back to the cold environment of interstellar space. These observations will reveal the timescales over which cometary outgassing ceases and the nucleus returns to its dormant state for the continuation of its galactic journey. The departure observations also offer opportunities to search for any debris or smaller fragments that might have separated from the main nucleus during its passage through the inner solar system. The detection of such fragments would provide additional targets for study and insights into the internal structure and cohesion of interstellar cometary nuclei. the study of stellar nucleosynthesis, the process by which stars create heavy elements in their cores, provides a theoretical framework for understanding what 3I Atlas's composition reveals about galactic evolution. When the universe emerged from the Big Bang, it contained only the lightest elements: hydrogen, helium, and trace amounts of lithium. Every element heavier than these primordial constituents was forged in stellar cores or during explosive stellar deaths, then dispersed into the interstellar medium where it could be incorporated into new generations of stars and planetary systems. The abundance patterns of elements in 3I Atlas therefore serve as a fossil record of the stellar populations that enriched its birth environment with heavy elements. Stars of different masses produce different ratios of elements. Massive stars excel at creating oxygen, silicon and iron, while intermediate mass stars contribute substantial amounts of carbon and nitrogen. The specific elemental and isotopic signatures preserved in 3I Atlas will reveal the mix of stellar types that contributed material to its formation region billions of years ago. This stellar archaeology becomes particularly powerful when we consider that 3I Atlas may predate our solar system by several billion years. During the epoch when this cosmic wanderer formed, our galaxy contained fewer generations of stars and consequently lower abundances of heavy elements. The metallicity, astronomical shorthand for the abundance of elements heavier than hydrogen and helium, of 3I Atlas's birth environment may have been significantly different from the conditions present when our solar system formed. Modern stellar evolution models predict how galactic metallicity has evolved over cosmic time, but these models require observational tests to verify their accuracy. Ancient objects like 3I Atlas provide direct samples of materials from earlier epochs of galactic evolution, offering crucial calibration points for theoretical models. The chemical composition of this interstellar visitor will either confirm current understanding of galactic chemical evolution or reveal discrepancies that require new theoretical insights. The process by which 3I Atlas was ejected from its birth system represents another fascinating aspect of planetary system dynamics. Current models suggest that most interstellar objects originate from gravitational interactions with giant planets during the early phases of planetary system evolution. As young planetary systems settle into their final configurations, close encounters between small bodies and massive planets can accelerate comets and asteroids to velocities that exceed the escape speed of their host systems. Jupiter and Saturn in our own solar system continue to scatter small bodies today, though at a much reduced rate compared to the violent early epochs of planetary system formation. The Oort cloud, a vast reservoir of comets surrounding our solar system, at distances of tens of thousands of astronomical units, consists largely of objects that were ejected from the inner solar system by planetary interactions, but remained gravitationally bound at enormous distances. Occasionally, these scattered objects receive additional gravitational kicks that push them beyond the escape velocity of the solar system entirely, sending them on journeys into interstellar space. Computer simulations suggest that our solar system has ejected far more objects than it has captured, contributing to the population of interstellar wanderers that includes objects like 3I Atlas. The efficiency of this ejection process depends on the architecture of planetary systems, the masses, orbits, and spacing of planets that determine how effectively they can scatter small bodies. Systems with massive planets in highly elliptical orbits prove particularly effective at ejecting material, while systems with planets in circular orbits tend to retain more of their small body populations. The properties of interstellar objects like 3I Atlas therefore provide indirect information about the typical architectures of planetary systems throughout the galaxy. Recent discoveries of exoplanetary systems have revealed a remarkable diversity of planetary architectures, many quite different from our own solar system. Hot Jupiters, gas giant planets orbiting very close to their stars, are common in other systems but absent from ours. Multiple planet systems often show orbital resonances and spacing patterns, unlike those in our solar system. This diversity suggests that planetary formation is a more varied process than early theories suggested, with different outcomes depending on the specific conditions present in individual protoplanetary disks. The study of 3I Atlas contributes to this broader understanding of planetary system diversity by providing samples of materials from systems that may have formed under different conditions than our own. If this visitor displays chemical signatures that differ significantly from solar system objects, it could indicate that its birth system had a different composition, structure, or evolutionary history than the environment where Earth and its sibling planets formed. The role of interstellar objects in galactic ecology represents an emerging area of research that considers how material exchange between stellar systems affects galactic evolution. Just as biological ecosystems involve flows of energy and nutrients between different components, galactic ecosystems involve flows of matter and energy between stars, planetary systems, and the interstellar medium. Interstellar objects like 3I Atlas participate in this galactic ecology by carrying material between star systems. While the mass transfer represented by individual objects is negligible, the cumulative effect of trillions of such objects over billions of years may play significant roles in galactic evolution. This material exchange could help homogenize the chemical composition of different galactic regions or facilitate the spread of complex organic molecules between stellar systems. The possibility that interstellar objects could transport living organisms between star systems, a concept known as panspermia, remains speculative but scientifically intriguing. While the harsh radiation environment of interstellar space makes survival challenging for most known life forms, some extremophile organisms on Earth can survive radiation doses and temperature conditions that approach those found in space. The detection of organic compounds in objects like 3I Atlas keeps these possibilities within the realm of scientific consideration. The deep time perspective that 3I Atlas provides extends far beyond the typical scales of human experience or even terrestrial geology. The age estimates placing this object at 7 to 14 billion years old span a significant fraction of cosmic history itself. When 3I Atlas formed, the universe was a very different place, smaller, denser, hotter, and containing fewer heavy elements than the cosmos we observe today. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old, but direct samples of materials from intermediate epochs between then and the formation of our solar system are extraordinarily rare. Ancient objects like 3I Atlas offer precious windows into these intermediate stages of cosmic evolution, preserving materials that formed when the universe was between 1/3 and 3/4 of its current age. During the epoch when 3I Atlas likely formed, the rate of star formation in the galaxy was much higher than it is today. More massive stars were being born and dying in supernova explosions, enriching the interstellar medium with heavy elements at a rapid pace. The galaxy's structure was also different, with a more pronounced thick disk component and possibly active interactions with satellite galaxies that have since been accreted or disrupted. The preservation of ancient materials in 3I Atlas across such vast timescales demonstrates the stability of certain chemical and physical processes under cosmic conditions. The survival of volatile compounds through billion-year journeys through interstellar space requires that the comet's internal structure and external environment remained within narrow temperature and pressure ranges throughout its travels. This preservation also implies that 3I Atlas's trajectory through the galaxy avoided close encounters with stars or other high-energy environments that could have disrupted its structure or altered its composition. The comet's current properties therefore provide constraints on the dynamical history of its particular path through galactic space, offering insights into the relative frequency of disruptive encounters in the galactic environment. Theoretical frameworks for understanding objects of such extreme age draw upon multiple disciplines, from stellar evolution and galactic dynamics to solid-state physics and astrochemistry. The behavior of materials under the conditions present in interstellar space, near absolute zero temperatures, intense radiation fields, and ultra-high vacuum conditions, differs significantly from terrestrial experience and requires careful theoretical modeling to interpret observational data. Laboratory experiments that simulate interstellar conditions provide crucial support for interpreting observations of objects like 3I Atlas. Researchers can subject ice mixtures and organic compounds to radiation doses and temperature cycles that approximate those experienced during million-year journeys through space, revealing how chemical composition and physical properties evolve under these extreme conditions. These experimental studies have revealed that organic compounds can become increasingly complex during prolonged exposure to cosmic radiation, forming elaborate molecular networks that might not develop under terrestrial conditions. The detection of complex organics in 3I Atlas could therefore represent not just preserved samples from its birth environment, but also the products of chemical evolution that occurred during its long journey through space. The connection between 3I Atlas and early universe conditions becomes particularly intriguing when we consider that this object may have formed when the cosmic environment was significantly different from today. The density of dark matter, the intensity of cosmic ray backgrounds, and the distribution of heavy elements throughout the galaxy have all evolved substantially over the past 10 billion years. The cosmic star formation rate peaked roughly 10 billion years ago, during an epoch that astronomers call cosmic noon, when galaxies were forming stars at rates far exceeding current levels. If 3I Atlas formed during this period of intense stellar activity, its composition might reflect the enhanced production of heavy elements and the more violent galactic environment that characterized this earlier cosmic epoch. The study of high redshift galaxies, distant systems that we observe as they existed billions of years ago, provides complementary information about the conditions present during 3I Atlas's formation era. These observations reveal galaxies with different chemical compositions, star formation rates, and structural properties than nearby systems, painting a picture of cosmic evolution that objects like 3I Atlas help ground in direct physical samples. Future observational campaigns planned for 3I Atlas will employ the most advanced astronomical instruments currently available or under development. The James Webb Space Telescope's unprecedented infrared capabilities will allow detailed spectroscopic analysis of the comet's outgassing, potentially detecting dozens of molecular species and measuring their relative abundances with high precision. Ground-based extremely large telescopes currently under construction, including the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will provide complementary observations with angular resolution and light-gathering power that exceed current capabilities. These instruments will be able to resolve fine structure within 3I Atlas's coma and tail, potentially detecting jets of material emanating from specific regions of the nucleus. Radio interferometer, arrays like ALMA and the Very Large Array, will search for emission lines from molecules that are difficult to detect at optical wavelengths, including complex organic compounds and simple molecules at very low abundances. These observations will provide the most complete inventory of 3I Atlas's chemical composition ever obtained for an interstellar object. Space-based missions specifically designed to study interstellar objects represent the next frontier in this field of research. The European Space Agency's Comet Interceptor mission, currently under development, is designed to rendezvous with and closely study a pristine comet from the outer solar system, or an interstellar visitor. While this mission won't reach 3I Atlas, it demonstrates the technological capabilities being developed for future interstellar object encounters. More ambitious mission concepts under consideration include high-speed interceptor spacecraft that could be rapidly deployed to rendezvous with newly discovered interstellar objects. These missions would require advanced propulsion systems and autonomous navigation capabilities to reach their targets during the brief windows when interstellar visitors are accessible from Earth. The technological challenges involved in such missions are substantial, but the scientific return would be transformative. Direct sampling of interstellar object materials and in situ analysis of their composition and structure would provide insights impossible to obtain through remote observation alone. Such missions could definitively determine the internal structure, precise composition, and formation history of these cosmic messengers. The broader implications of 3I Atlas research extend to fundamental questions about the prevalence and diversity of planetary systems throughout the galaxy. If detailed study reveals that this visitor formed under conditions very similar to those in our solar system, it would suggest that the processes of planetary formation follow similar patterns around different types of stars in different galactic environments. Alternatively, if 3I Atlas displays compositional signatures that differ significantly from solar system objects, it could indicate that planetary formation is more diverse than current theories suggest, with different outcomes depending on local conditions in individual stellar systems. Such diversity would have important implications for the potential habitability of exoplanets and the likelihood of finding life elsewhere in the galaxy. The statistical properties of interstellar object populations will become increasingly important as future surveys detect larger numbers of these visitors. The size distribution, compositional diversity, and frequency of detection will provide insights into the efficiency of ejection mechanisms in different types of planetary systems and the survival rates of different materials during interstellar travel. Current estimates suggest that interstellar objects may be passing through the inner solar system at rates of several per year, though most are too faint to detect with current survey capabilities. The Vera Rubin Observatory's legacy survey of space and time, beginning operations in the mid-2020s, should detect dozens of interstellar objects annually, transforming this field from the study of individual rare events to the statistical analysis of populations. Educational initiatives surrounding 3I Atlas have demonstrated the powerful appeal of interstellar visitors for inspiring public interest in science and astronomy. The concept of visitors from other star systems resonates with fundamental human curiosity about our place in the universe and our relationship with the cosmic environment beyond Earth. These objects serve as tangible reminders that we are part of a vast galactic community connected through the constant exchange of matter and energy. The international collaboration required to study 3I Atlas also demonstrates science's potential to unite researchers across national and cultural boundaries in pursuit of common goals. The rapid coordination of observational campaigns, data sharing, and theoretical analysis that characterizes interstellar object research exemplifies how the scientific community can respond effectively to rare opportunities for discovery. As 3I Atlas continues its approach toward perihelion, the intensity of scientific interest will only increase. The peak activity period around closest solar approach represents the optimal opportunity for detecting trace constituents and measuring precise isotopic ratios that will provide the deepest insights into this object's origin and evolution. Every new measurement adds another piece to the puzzle of understanding, not just this individual visitor, but the broader population of interstellar objects and their role in galactic evolution. The legacy of 3I Atlas research will extend far beyond the immediate results of current observations. The methodological advances, technological developments, and theoretical insights emerging from this study will benefit astronomy and planetary science for decades to come. Future discoveries of interstellar objects will build upon the foundation established through the careful study of this remarkable cosmic messenger. In the gentle dance of light and shadow, gas and dust that surrounds 3I Atlas, as it awakens under our sun's warming rays, we find encoded the deepest stories of cosmic evolution, tales of stellar birth and death, of planetary formation and destruction, of the patient processes that have shaped our galaxy over billions of years of cosmic time. This ancient traveller carries within its frozen nucleus not just the chemical signatures of another world, but the accumulated history of our cosmic neighbourhood across epochs that span significant fractions of the age of the universe itself. As we reach the final chapter of our journey through the 100 facts that paint the portrait of 3I Atlas, we move beyond the realm of direct observation and careful measurement into something more profound, the realm of wonder, speculation, and cosmic meaning. Here, in this space between what we know and what we can only imagine, we encounter the deepest truths about what it means to share our galaxy with ancient wanderers from other star systems. Try to imagine the patience of interstellar space. While we measure our lives in decades and human civilization in millennia, 3I Atlas has been drifting through the cosmic dark for periods that dwarf all of recorded history. Millions of years ago, when our earliest ancestors were taking their first tentative steps upright on African plains, this wanderer was already old in its journey, moving silently through regions of space so empty that the distance between particles rivals the emptiness we find in the most perfect terrestrial vacuums. Through ice ages and warm periods, through the rise and fall of species on countless worlds that may orbit distant stars, 3I Atlas has maintained its course, a cosmic voyager carrying stories from stellar neighborhoods we will never visit. Its journey spans not just space but time, vast epochs during which entire civilizations might have risen and fallen on worlds we can barely imagine, while this patient traveller continued its silent passage through the darkness between suns. The loneliness of this journey defies human comprehension. For millions of years, 3I Atlas has known no warmth save the faint glow of distant stars, no gravitational embrace save the gentle pull of the galaxy itself. It has passed through regions where the nearest star might be dozens of light years away, drifting in darkness so complete that even the combined light of all the stars in the galaxy barely illuminates its ancient surface. Yet there is also freedom in this cosmic wandering, liberation from the gravitational bonds that tie most objects to their birth systems, freedom to explore the galaxy in ways that no planet-bound observer ever could. 3i Atlas has witnessed our galaxy from perspectives denied to us, seeing star clusters and nebulae from angles impossible to achieve from any single stellar system, carrying within its nucleus a kind of cosmic memory of the spaces between worlds. The birth system that once called 3i Atlas home remains forever unknown to us, lost in the vast catalogue of stellar possibilities that populate our galaxy. Was it a system much like our own, with rocky inner planets and gas giants in the outer reaches? Or did this visitor emerge from an environment utterly alien to our experience? Perhaps a system with multiple stars, or massive planets in eccentric orbits that created a chaotic gravitational environment from which escape was common. We can only speculate about the circumstances that sent 3i Atlas on its interstellar journey. Perhaps it was a close encounter with a massive planet that flung it outward at escape velocity, or a gravitational interaction during the passage of a nearby star that disrupted the outer regions of its birth system. Maybe it escaped during the violent early epochs of planetary formation, when giant impacts and orbital migrations made the outer reaches of stellar systems unstable and dangerous places for small bodies. The star around which 3i Atlas formed may no longer exist, having evolved and died during the billions of years since this comet began its journey. If that star was more massive than our Sun, it might have swelled into a red giant and then collapsed into a white dwarf neutron star or black hole, leaving only gravitational echoes of the planetary system that once nurtured this cosmic wanderer. Alternatively, that distant sun might still burn in some far corner of the galaxy, perhaps warming worlds that never knew they once had a sibling now wandering among alien stars. The siblings that 3i Atlas left behind, the other comets, asteroids, and perhaps planets that shared its birth system, have followed very different evolutionary paths. While our visitor has spent eons in the cold depths of interstellar space, those left behind have continued to evolve within their original stellar environment, shaped by billions of years of additional planetary interactions, tidal heating, and stellar radiation. If planets formed in that distant system, they might now host their own forms of life, unaware that pieces of their world once travelled the galaxy as cosmic messengers. The water that may have comprised part of 3i Atlas's ice could have fallen as rain on alien continents, filled alien oceans, or nourished alien life forms that developed in complete independence from terrestrial biology. The chemical elements that make up 3i Atlas, the carbon, oxygen, silicon and iron forged in stellar cores and dispersed by supernovae, represent recycled stellar material that has participated in multiple cycles of cosmic evolution. These atoms may have been part of earlier generations of planets and comets, scattered by stellar explosions and gravitational disruption, only to be reassembled into new worlds around younger stars. In this sense, 3i Atlas carries within its nucleus not just the memory of its immediate birth system, but the accumulated history of stellar generations stretching back billions of years into the galaxy's past. Each atom tells a story of stellar nucleosynthesis, of the patient alchemy by which hydrogen and helium are transformed into the complex chemistry that makes rocky planets and carbon-based life possible. The organic compounds detected in 3i Atlas represent particularly tantalizing links to the broader story of cosmic chemistry. These complex molecules, formed through radiation processing during the comet's long journey through space, demonstrate that the building blocks of biological complexity can arise and persist under the most extreme conditions imaginable. While these organic compounds are far simpler than the biochemistry of living organisms, they occupy a crucial position on the spectrum between simple stellar chemistry and the molecular complexity that characterizes life. The presence of such compounds in an object from another star system suggests that the chemical pathways leading toward biological complexity may be common features of galactic evolution rather than unique accidents of terrestrial chemistry. The possibility that 3I Atlas might carry actual living organisms, dormant during its interstellar journey, but potentially revivable under the right conditions, remains within the realm of scientific speculation. While the harsh radiation environment of interstellar space makes survival challenging for most known life forms, some extremophile organisms on Earth have demonstrated remarkable resilience under conditions that approach those found in space. The concept of panspermia, the transfer of life between stellar systems via objects like comets and asteroids, has a long history in scientific thought, from the speculations of early astronomers to modern astrobiological research. While we have no evidence that 3I Atlas carries living passengers, the mere possibility adds layers of meaning to its passage through our solar system. If life has indeed spread between star systems through cosmic messengers like 3I Atlas, then the appearance of this visitor might represent more than just a rare astronomical event. It could be part of an ongoing process of biological exchange that connects living worlds across galactic distances. The implications of such connections stretch the imagination, suggesting forms of cosmic ecology that operate on scales vastly exceeding anything in terrestrial experience. The trajectory that will carry 3I Atlas away from our solar system and back into interstellar space represents another journey of unimaginable duration. Current calculations suggest that this cosmic wanderer will eventually encounter the gravitational influence of other stars, possibly passing through their outer planetary regions and potentially delivering samples of our solar system's chemistry to alien worlds. The dust and gas that 3I Atlas is currently shedding as it approaches the Sun will become part of the solar system's inventory of small particles, eventually settling onto planetary surfaces or being swept away by the solar wind. In this way, our interstellar visitor leaves behind a subtle signature of its passage, mixing materials from another star system with the local chemistry of our cosmic neighborhood. Billions of years from now, when our Sun has evolved into a red giant and the current configuration of the solar system no longer exists, 3I Atlas will still be journeying through interstellar space. It might encounter other star systems, possibly triggering the same excitement among alien astronomers that its arrival has generated here on Earth. Those distant observers might conduct their own analyses of this ancient wanderer, perhaps detecting chemical signatures that reveal something about the solar system and the epoch of galactic history it represents. The timescales involved in 3I Atlas's journey challenge our usual concepts of permanence and change. While human civilizations rise and fall over periods of centuries or millennia, and even geological processes operate over millions of years, the journey of interstellar objects spans billions of years, periods so vast that they approach significant fractions of cosmic time itself. During the remaining lifetime of our galaxy, 3I Atlas might encounter dozens of other star systems, serving as an inadvertent ambassador, carrying information about each stellar environment it visits. The cosmic wanderer that we are studying today might eventually accumulate layers of material from multiple stellar encounters, becoming a kind of interstellar time capsule that preserves samples from many different epochs and locations in galactic history. The gravitational interactions that will govern 3I Atlas's future trajectory operate according to the same physical laws that shape the orbits of planets and the structure of galaxies, yet their outcomes over such vast timescales become unpredictable in detail. While we can calculate the comet's path for the next few million years with reasonable accuracy, longer-term predictions become increasingly uncertain as small gravitational perturbations accumulate into large changes in trajectory. This unpredictability reflects a fundamental aspect of complex dynamical systems, their sensitive dependence on initial conditions that makes long-term prediction impossible despite the deterministic nature of the underlying physical laws. The future journey of 3I Atlas will be shaped by countless chance encounters with stars, gas clouds, and other objects whose precise positions and velocities cannot be predicted over billion-year timescales. The scientific legacy of 3I Atlas extends far beyond the immediate observations and analyses that characterize its current passage through our solar system. This visitor has already transformed our understanding of interstellar objects and their role in galactic evolution, while establishing methodological frameworks that will guide the study of future cosmic messengers. Future generations of astronomers will look back on the detection and characterization of 3I Atlas as a pivotal moment in the development of interstellar object science. The rapid response networks, international coordination, and multi-wavelength observational campaigns that have characterized the study of this visitor represent new paradigms for how the astronomical community responds to rare and time-limited opportunities for discovery. The technological advances driven by the need to extract maximum scientific information from limited observations of 3I Atlas will find applications throughout astronomy and planetary science. The development of more sensitive spectrographs, improved data analysis algorithms, and enhanced international coordination systems will benefit many areas of research beyond the study of interstellar visitors. Educational and outreach programs centered on 3I Atlas have demonstrated the unique power of interstellar objects to capture public imagination and communicate the excitement of scientific discovery. The concept of visitors from other star systems resonates with fundamental human curiosity about our place in the universe and our relationship with the cosmic community beyond Earth. The cultural impact of discovering authentic visitors from other star systems touches on some of humanity's deepest questions about cosmic loneliness and connection. For most of human history, Earth seemed isolated in space, surrounded by distant stars that might as well have been painted on a celestial sphere for all the contact they had with our world. The arrival of objects like 3I Atlas provides tangible evidence that we are part of a connected galactic community where matter and energy flow between stellar systems. This realization carries philosophical implications that extend far beyond astronomy. If our solar system is constantly receiving visitors from other stellar neighborhoods, and if we are similarly contributing objects to the interstellar population, then Earth exists within a cosmic ecosystem characterized by ongoing exchange and interaction rather than isolation and separation. The patience required to study objects like 3I Atlas reflects broader themes about the relationship between human timescales and cosmic timescales. While our individual lives span mere decades and our civilizations persist for centuries or millennia, the cosmic processes that shaped 3I/Atlas operate over periods measured in billions of years. This vast disparity in timescales creates both humility and wonder. Humility because it reminds us how brief our existence is relative to cosmic history, and wonder because it reveals that we are capable of understanding and appreciating processes that vastly exceed our personal experience. In studying 3I Atlas, we demonstrate the remarkable ability of conscious beings to transcend the limitations of their immediate circumstances and participate intellectually in the grandest scales of cosmic evolution. The mathematical precision with which we can calculate 3I Atlas's trajectory and predict its future behavior represents one of humanity's greatest intellectual achievements. The discovery that the universe operates according to comprehensible physical laws that apply equally to terrestrial experiments and cosmic phenomena. The same gravitational principles that govern falling apples also determine the paths of interstellar comets across galactic distances. This universality of physical law provides the foundation for our confidence that the chemical analyses we perform on 3I Atlas's spectral emissions reveal genuine information about its composition and origin. The atomic and molecular processes that create spectral lines operate identically throughout the universe, allowing us to analyze the chemistry of objects that formed in other star systems billions of years ago. The aesthetic dimension of 3I Atlas's story, the simple beauty of a cosmic wanderer journeying between star systems, touches on aspects of experience that transcend purely scientific analysis. There is something profoundly moving about the image of this ancient object, maintaining its course through the darkness, carrying within its nucleus the chemical memories of worlds we will never see. This aesthetic appreciation reflects a fundamental aspect of human nature, our tendency to find meaning and beauty in natural processes that operate on scales far exceeding our immediate concerns. The story of 3I Atlas connects us to the grandest narratives of cosmic evolution, while remaining grounded in the tangible reality of an object we can observe and analyze with our instruments. As 3I Atlas continues its approach toward perihelion and eventual departure from our solar system, we are privileged to witness a cosmic drama that unfolds over time scales both vast and brief. Vast, because this visitor has been journeying for millions of years to reach us, and brief, because our opportunity to study it will last only months or years before it continues its journey into interstellar space. This temporal paradox, the intersection of geological timescales with human observation periods, creates a sense of urgency and preciousness around every measurement and observation. We're experiencing a rare cosmic coincidence, a moment when an ancient wanderer from another star system happens to pass close enough to Earth for detailed study during the brief epoch when human civilization has developed the technological capability to appreciate its significance. The future departure of 3I Atlas will mark the end of our direct observational access to this remarkable object, but not the end of its scientific legacy. The data collected during its passage will continue to yield insights for decades as analytical techniques improve and theoretical understanding advances. Future discoveries of similar objects will benefit from the methodological groundwork established through the study of 3I Atlas. In a broader sense, 3I Atlas represents just one thread in the vast tapestry of cosmic evolution that connects all matter and energy throughout the universe. The atoms that comprise this interstellar visitor were forged in stellar cores, dispersed by supernovae, and reassembled into planetary systems multiple times during the galaxy's history. The same processes that created 3I Atlas also created Earth, the Sun, and ultimately the complex chemistry that made life and consciousness possible. This cosmic perspective transforms our understanding of what it means to encounter a visitor from another star system. We are not separate beings observing an alien object, but rather temporary patterns of organized matter studying another temporary pattern that happens to have originated in a different stellar environment. The same cosmic processes that shaped 3i Atlas also shaped us, creating a fundamental kinship that transcends the vast distances and time scales involved. The gentle passage of 3i Atlas through our solar system serves as a reminder that the universe is neither hostile nor indifferent, but rather characterized by the same physical processes and chemical evolution that made our own existence possible. This ancient wanderer brings greetings not from alien intelligence, but from the cosmic processes of planetary formation and stellar evolution that operate throughout our galaxy. As we prepare to bid farewell to this cosmic messenger, we carry with us a transformed understanding of our place within the galactic community. We are not isolated on a lonely planet, orbiting an insignificant star, but rather participants in a vast network of matter and energy exchange that connects all stellar systems across the galaxy. The arrival of 3i Atlas provides tangible evidence of this connection, demonstrating that our solar system exists within a dynamic galactic ecosystem characterized by ongoing interaction and exchange. The story of 3i Atlas ultimately becomes part of our own story, the continuing human adventure of exploring and understanding the cosmos that gave birth to us. In studying this visitor from the stars, we participate in one of science's most fundamental activities, using careful observation and analysis to understand our place within the vast, ancient, and ever-evolving universe that is our home. The 100 facts we have explored together paint a portrait not just of a single interstellar object, but of the cosmic processes that connect all matter throughout space and time. In the patient journey of 3i Atlas across the galaxy, we find reflected the patient journey of consciousness itself. From the simple chemistry of stellar nuclear synthesis to the complex organization of matter that allows the universe to observe and understand itself through beings like us. As this ancient traveler continues its journey back into the darkness between stars, it carries with it not just the chemical signatures of our solar system, but also the invisible signatures of human curiosity and wonder that have characterized its brief visit to our cosmic neighborhood. In return, it leaves us with expanded understanding, deeper appreciation for cosmic connections, and renewed sense of participation in the grandest story ever told, the continuing evolution of matter, energy, and consciousness throughout our magnificent, interconnected universe. And so our gentle journey through 100 facts about 3i Atlas comes to a close. Somewhere out there in the darkness between Mars and Jupiter, this ancient wanderer continues its patient approach toward the sun, carrying within its frozen nucleus the stories of another star system and another era of cosmic history. Thank you for drifting with me tonight through the remarkable tale of our third interstellar visitor. Whether this journey has helped you find rest or filled you with quiet wonder at the cosmic messengers that travel between the stars, I'm grateful you joined me among the facts that reveal the universe's hidden connections. If you're still listening and enjoyed this cosmic exploration, please consider subscribing to the Sleepy Astronomer for more gentle journeys through space, time, and the peaceful science of sleep. Your support helps me continue creating these contemplative adventures through the cosmos. Sweet dreams and clear skies. This is the Sleepy Astronomer, wishing you the most peaceful rest under the same stars that have guided 3i Atlas on its billion-year journey to our cosmic doorstep.